All right, so today we're going to talk about a couple of more op-amp configurations and then start talking about non-idealities. We're going to wrap up today, I think, with just input offset voltage, which will be enough for you guys to do all of your homeworks. And then on Friday, we're going to talk about further non-idealities like input bias current, slew rates, gain bandwidth, product, all that kind of jazz. All right, so first things first, we are going to talk about, or let me make sure in chat here that it's just everybody saying they are here. And it does appear to be the case. All right, we're on page 1, things are looking great. So our first thing that we're going to talk about is a logarithmic amplifier. And a logarithmic amplifier is our basic negative feedback amplifier. We have an input resistance between our input voltage and the inverting input terminal of our op-amp. We are going to ground the non-inverting input terminal. And then here in our feedback loop is where things are going to get a little wild. And over here is our output. So a logarithmic amplifier places a NPN BJT into our feedback loop. Now we could actually do this with a PNP BJT as well, but the characteristics are going to be a little bit different. So just to be clear, because it's been a hot minute since we've looked at BJTs, this is our collector, this is our base, and down here is our emitter. So the direction for our collector current is as follows. All right. So let's first look at this guy with an ideal or infinite open loop gain. Dang it, my stupid thumb's getting in the way. So when A naught is equal to infinity, what that means is that the voltage here at node X is equal to 0 because there's no difference between our VN1 and VN2, or the non-inverting input voltage and the inverting input voltage. And so all of the current that we are going to see that flows through that resistor R must continue on and flow into the collector terminal of our BJT. So we can say that Vn divided by R is equal to our collector current IC. And we can recall, hopefully, from 335 that we can express the base emitter voltage for a an NPN BJT transistor as VT natural log IC over IS. Well, if we substitute in our previous relationship, this becomes Vn over R times IS. You may be thinking to yourself, well, how on earth does this help me? Our output voltage So we can see that the positive polarity output voltage would be like this. It's a nodal voltage, so the positive polarity is on the terminal labeled V out. The negative polarity terminal is inherently at ground. So V out is the exact same thing as VEB, because the base of our transistor is connected to ground. So V out is VEB, which is the exact same thing as negative VBE, right? If I change the order of my subscript, that is the exact same thing as multiplying the signal by a factor of -1. And so with this realization, we can then see that V out is equal to negative VT natural log of Vn over R times Is. So we have an amplifier wherein the output voltage signal is proportional to the natural logarithm of the input voltage signal. So let's talk for just a moment about how this thing works, because it may seem a little bit funny and it's going to lead us to a realization as well. So our base is permanently grounded in this configuration. So in order for this BJT to conduct current, what does that tell us about the output voltage? It's always going to be negative, right? And the more current we want this guy to push through, the more negative that output voltage is going to get. So this gives us a constraint that Vn must always be a positive or 0 or greater quantity. And mathematically, that has to be the case as well. We can't take the natural logarithm of a negative number. Best case scenario, when we take the natural logarithm of a number that is a fraction or smaller than 1, you get negative values. When it's greater than 1, you get positive values. And when it's negative, it is undefined. So mathematically, it's we are told that Vn can't be less than 0. And it makes sense that Vn can't be less than 0 or this guy starts acting oddly. So let's talk about what that odd behavior is real quick. What happens if Vn is less than 0? That transistor turns off, right? Cannot conduct current, so it looks like an open circuit. So if the feedback loop is thrown away, we now have an open loop circuit. Do you guys remember how open loop circuits behave from back in circuits 2 when you had me a couple of years ago? Output voltage was always at the positive power supply or the negative power supply, right? So effectively all of that near infinite open loop gain gets applied to whatever signal you have at the input. In this case, a negative input signal would cause our output to swing to the positive supply rail. So our output would go towards VCC plus. So let me write that down. So this V out right here is valid only for Vn greater than or equal to 0. And it is equal to VCC plus when Vn is negative, right? So we now pretty thoroughly understand what's going on here. A good question that you guys may ask is, well, why the heck would we ever care to have an amplifier with a logarithmic relationship between the input and output signals? So what we're going to do real quick is we are going to get what's called the small signal gain of this guy and see how it works. So for our small signal gain, if I can stop accidentally opening up Windows, we are going to take the derivative with respect to the input voltage of both sides. So V out will be equal to the derivative with respect to the input voltage of negative VT natural log Vn over R times Is. So this is going to look like dV out over dV in is equal to d by dV in of negative Vt times the natural logarithm of Vn minus the natural logarithm of R times Is. So whenever I have two, or whenever I have a fraction, I can split it up into two things and subtract. And I can write this a little bit better. Partial with respect to Vn of negative Vt natural log Vn plus partial with respect to Vn of positive Vt natural log R times Is. Everything in that rightmost term is a constant, right? Vt is a constant, R is a constant, Is is a constant, so we're taking the derivative of a constant value. This whole guy goes to 0. What's the derivative of the first term? So we have some constant value multiplied by the natural logarithm of Vn. So what's the derivative of natural log? 1 over Vn, right? So we get our small signal voltage gain, AV, partial of V out with respect to Vn is just negative Vt over Vn. So if we plotted this guy, here is Vn, and here is the magnitude, because I just want to deal with positive numbers for now. It's going to look, if I could draw without my hand shaking so much. Something like this, where we see that as Vn increases, the magnitude of AV decreases. This means that weak signals experience a lot of gain and strong signals experience a small amount of gain. This is what's known as compression. Very, very common in audio amplifiers. So in an audio amplifier, what compression is used to do is to effectively flatten out peaks. So like I play guitar, I'm sure all of you that have been in my office have noticed I've got guitars and all that kind of crap and amps and just dumb shit all over the place. And so what a compressor amplifier does is it effectively smooths out the audio signal so that when you're playing really heavily, all those peaks don't hit the amplifier very hard, and when you're playing very lightly, they're brought up so that the overall output level of your playing is effectively consistent. Another place that you might see this is, how many of you guys watch like video podcasts or any kind of stuff like that? So a compressor would be used on the voltage track, or excuse me, on the vocal track of that, because as a person moves closer to a microphone, the signal should increase, and when they move further away, the signal should decrease. If you use the compressor, it's all at relatively the same volume because of the way it amplifies weaker signals and amplifies less so stronger signals. So compression's actually a very, very useful tool. So now let's make things marginally harder on ourselves and see what happens when the amplifier is not ideal, right? So in the previous case, we considered an infinite gain. Now let's look at when we have a non-infinite gain. So we're going to have the same basic relationships. The only change that we're going to see is that we're not guaranteed that Vx is 0 anymore, right? So from our characteristic equation, we know that Vout is going to be negative our open loop gain times Vx, because that's true for all non-ideal negative feedback op-amp circuits, which gives us Vx is equal to negative Vout over A naught. Setting our currents to be equal, we're going to have Vn minus Vx over R is equal to our collector current IC. Again, our base emitter voltage is then Vt natural log of IC over Is, which gives us Vn minus Vx over RIS, and recognizing that Vout is equal to VEB is equal to negative VBE, we get Vout is equal to negative VT natural log Vn plus Vout over our open loop gain divided by R multiplied by Is. So having a non-ideal open loop gain causes some small amount of gain error. This one is a lot harder to directly quantify because it's buried inside that natural logarithmic function. So I'm going to leave it like this because it's terrifying to try to do that math and decouple everything. All right, so when we put a BJT in our feedback loop, we got a logarithmic amplifier because of the exponential relationship between the collector current and the voltage VBE. So now we're going to look at an amplifier where we have a MOSFET in the feedback circuit. Output. All right, so let's start with an NMOS transistor. Like so. Here is our drain, here is our gate, here is our source, and this is our drain current ID. In this direction, let's call this guy R right here. So before we saw that we had the inverse of the relationship between the current and the voltage. We're going to have the exact same thing here. So the drain current in a MOSFET transistor is related to the square of the input voltage VGS. So we're going to have a square root amplifier now because it's the opposite thing. All right, so what can you guys tell me about how, if we are considering this circuit to have an infinite open loop gain, how is this MOSFET connected? Not what I'm looking for. So what is the potential at the gate? 0. What's the potential at the drain? It's 0. So what kind of transistor connection do we have if the gate and the drain are at the same potential? Because these are both always going to be at 0 if we consider an infinite open loop gain. Is it a diode connected or is it a current source? Diode connected, right? Okay, so we have a diode connected MOSFET, NMOS transistor here. The gate and the drain aren't directly tied together, but it's going to behave as if it were diode connected because this node, Vx, will always be at 0 volts, which is the same potential as the gate for an infinite open loop gain. So for a diode connected MOSFET, what region of operation is it forced to be in at all times? Saturation, triode, or cutoff? It's got to always be in saturation because VGS is equal to VDS. So VDS will always be greater than VGS minus VTH. VGS is always greater than VGS minus VTH, okay? So this guy is always going to be in saturation. So let's say I applied a voltage of 0 volts to the input. What does that force V out to be, since this guy has to be operating in saturation? Think about this for a second, right? If I apply a voltage of 0 volts to V in, how much current is flowing through that resistor R? None. So how much current is flowing through our transistor? Also none. So that means that this guy is in saturation, but it's on the edge of turning on or exiting the cutoff region. So V out has to be equal to exactly negative VTH. Okay, so it's forcing our output voltage to be at negative VTH so that this guy, the transistor, is on, but no current is flowing. All right. As our voltage increases, ID increases, and it's driving that voltage V out below VTH to compensate for that increase in current that's flowing through the system. All right. So it's a very similar operation to how the logarithmic amplifier worked, but the relationship between the current and the voltage is going to be slightly different because it's a MOSFET transistor versus a BJT transistor. Same basic theory of operation. As V in goes up, current gets larger, causes V out to get more and more negative. It's just that mathematical relationship is going to be a little bit different. So let's investigate the mathematical relationship now. So this is, again, strictly for A naught is equal to infinity. We are going to see that our current Vn over R1 has to equal our drain current of 1/2 mu n C aux W over L times VGS minus VTHN quantity squared. And we're going to ignore channel length modulation because well, it's just going to make the math really, really hard. So I don't want to do it. That's the short answer. It's just going to make it awful. Our output voltage, if I can stop randomly pressing buttons, is VSG, right? Positive polarity of the output voltage is tied to the source. The negative polarity is at ground, and ground is the gate potential here. So V out is equal to VSG, which is negative VGS. And we can now substitute this relationship into our prior one and figure out our input-output relationship. So with that in mind, we will have Vn over, oh, I don't know why I keep writing R1. There's only one resistor, so I haven't labeled it. I apologize. Vn over R is equal to 1/2 mu n C ox W over L, negative V out minus VTHN, quantity squared. So now I'm going to multiply both sides by a factor of 2, divide both sides by a factor of mu n C ox W over L, and what I get is twice Vn divided by R mu n C ox W over L is equal to negative V out minus VTHN squared. So I can take the square root of both sides, and this gives me negative V out minus VTHN is equal to the square root of twice Vn divided by R un C ox W over L. And finally, I get V out is equal to negative VTHN. So we knew that it was going to have that offset from what we talked about earlier. It had it for Vn is equal to 0. The output voltage has to be at negative VTH minus the square root of 2 Vn over R mu n C ox W over L. Are there any restrictions on our input voltage? Let's look back up here, see if we can figure things out. Or we can look at the mathematical formula. Either way works. So what happens if Vn is negative mathematically? Our output voltage is undefined, right? In the circuit itself, here's where things can maybe get a little bit confusing, right? So a MOSFET transistor is inherently a symmetrical device. So what we should expect is that our current should start flowing in the opposite direction because the source and the drain trade places. However, the drain, nominal drain right here, is at a potential of 0, and the gate is at a potential of 0. The drain, if the source and the drain switch places, we would no longer have a diode connected MOSFET, so it's no longer forced to be in the saturation region. It's instantly going to go into cutoff whenever our input voltage goes negative, which breaks our feedback loop. And again, we have an open loop amplifier where a negative input voltage corresponds to an output voltage of VCC plus, or a positive power supply. Does that make sense? So it seems like the current should just flow the other direction, but we no longer have our diode connected transistor, which means we're no longer guaranteed saturation operation. All right, so this is valid for Vn is greater than or equal to 0 volts. And we have VCC plus for Vn is less than 0 volts. All right. That guys seem fairly straightforward. So what happens if we put a PMOS transistor in here? All right. So first, I want you guys to help me identify which are the correct terminal labels for this PMOS transistor. Okay, because the only thing that changed between our previous drawing and this one is the direction of the arrow. Okay. So in this case, the arrow, or for a MOSFET transistor, or specifically, the schematic model, or the schematic representation that we are using, the arrow always denotes the source, right? We're using enhancement mode MOSFETs, so the arrow is always at the source. So then that guy is the drain, and this guy is the gate. So we have the exact same terminals as we had before. Now, I don't use that hippie weirdo drain current for PMOSs that majority of you guys use, so I probably need to explain what I'm about to do. For those of you that were in my section of 335, you can, I don't know, take a nap for 5 seconds. For a, let's see, drain, source, gate, our drain current was in this way, was in this direction, and we had 1/2 mu n C ox W over L VGS minus VTH n quantity squared, okay? That was common between both of the classes. For a PMOS transistor, the source is the location of the highest potential. The drain is at the lowest potential, and here's our gate. And you guys learned it with the current flowing in the up direction for whatever hippie weirdo reason, which makes no sense whatsoever to me. And then involved having lots of negative signs and weird crap like that, and potentially absolute value signs. And I think that's hot garbage because I can't remember all that crap, and I have a doctorate in this dumb stuff. So instead, we can say that the drain current direction down, so that the drain current is always flowing from the location of high potential to low potential, which is how you learned about currents in engineering 120. So it doesn't make any damn sense to change it when you're a junior. We get the following relationship. No. 1/2 mu p C ox W over L VSG minus VTHP quantity squared. That's it. Change the subscripts. That's all it takes. Now all of these quantities have positive values. VTH has a positive value. VSG will have a positive value. If you included channel length modulation, VSD would have a positive value. You no longer have to carry around and worry about a bunch of dumb negative signs that always confuse me and I forget them. So to me, this is much, much easier. This is what I'm going to be doing. Okay. So with that in mind, this is the direction of our drain current in this particular circuit, right? It's flowing from the high potential source to the low potential drain. Right? And we can already inherently see then, this is a diode connected PMOS circuit, right? Because the drain and the gate are tied to the same potential of ground. And so when Vin is equal to 0, Vout must inherently be VTHP higher than ground for our PMOS transistor to have to be in saturation and about to conduct current in that direction. Okay, so this guy is going to behave exactly the same as our previous thing, except we're going to have negative signs. Everything is effectively going to be multiplied by a negative number. So our output voltage relationship, V out, not going to go through the derivation here because it's effectively the exact same operation, is going to be positive VTHP plus the square root of negative twice Vn divided by R mu P Cox W over L, where Vn has to be less than or equal to 0 volts. So our input voltage always needs to be negative or 0. And our output voltage is VCC minus, or the negative supply voltage, when Vn is positive. So all of these transistor circuits with a transistor in the feedback loop, whenever the feedback loop breaks open because the transistor is off, this becomes an inverting comparator. This is what's going on. So. All right. So any questions on these last couple of amplifiers? I know they're a little bit wonky looking, but they are actually rather useful. Not going to bother with the non-ideal cases in these. Math gets brutally weird, and at no point whatsoever in your textbook are you asked to do it, not even any of the problems in the back of the chapter. So I'm not going to do it either. All right, so our next thing to consider then is op-amp non-idealities. And this is really going to cover many of the things, like we've already been dealing with the non-ideality of when the open loop voltage gain is finite. But here we're going to talk about what happens when the input resistance is finite, when the output resistance is finite, when the speed at which the op-amp can process a signal is finite and stuff like that. But the first thing that we're going to talk about is a little bit easier to grasp what's going on, and it's called, the DC offset voltage. So I want you guys to consider the following circuit. Think really hard about the answer. For such a configuration, what should V out be? 0, right? So if we have no difference between our input terminals because they are literally tied to the same voltage, in this case, I chose to use ground because I'm not yet ready to talk about common mode signals and all that kind of jazz. But if Vn1 is 0 and Vn2 is 0, V out is supposed to be our open loop voltage gain times the difference, which is 0. However, in practice, we may see that the output voltage isn't 0. It's not going to be particularly large, but it will be non-zero. The reason that this occurs is because the transistors that are used at the input stage of the op-amp, forming the differential pair, which is something we're going to be talking about in, I think, in chapter 10, may be mismatched, meaning that for a BJT transistor, they might see a slightly different voltage VBE at their inputs, which is giving rise to a little bit of current, which is causing a voltage further downstream. Or in a MOSFET transistor, it could be due to the transistors are not literally exactly the same size, right? So if the W over L ratios are not precisely the same due to some manufacturing error, you'll wind up getting a small voltage seen at the output. In order to correct for this, there are usually terminals added on your op-amp. So like I think way back in circuits 1, I described an op amp as a 7-terminal device, 4 of which we were going to ignore. Okay. So for, just as a quick aside, for a generic op amp, most packages, we have our non-inverting input terminal, our inverting input terminal, and our output terminal. Those are the ones that we've been using all the time, right? All the way from circuit 1. In circuits 2, for sure, we made mention of the positive and negative power supply terminals. Well, there are also 2 more terminals, and these are used as DC offset null. In fact, let me bring up something real quick here. Dropbox, there we go. 223, and I think I started harping about this in the winter of 2019. Open. For those of you on Zoom, can you see my screen if you're paying attention? No one's paying attention. Great. Oh, somebody is paying attention. Yes, okay, great. So if we scroll all the, well, we can see it here. Offset null 1 is on pin 1, offset null 2 is on pin 2. No big deal there. But when we scroll down here, here's my functional block diagram. There's circuitry in here specifically to be able to apply a small voltage to either pin 1 or pin 2, or typically speaking, actually, you would put a potentiometer between those two and be able to, with a voltage on one of the legs, and be able to adjust the ratio of the resistances to zero out the offset on both of the pins simultaneously. But anyway, there is some circuitry in there specifically for getting rid of this small offset voltage, because particularly in BJT amplifiers, it can be large enough to cause really, really big problems in some specific applications. So that is a simplified diagram of an op amp with 22 transistors. So, we're going to learn about an awful lot of these guys, actually. So over there at the input, that's what's called a differential pair. It's being loaded. So there's a diode connected PNP BJT up there at the top. That's what's loading in, getting our power supply voltage. Down here at the bottom, we have current mirrors, all kinds of good stuff. You're going to learn about the building blocks of almost all of this in this class. So, all right, so we can get rid of this. Just wanted to explain what was what. Okay, so DC offset voltage. All right, so we have a mismatch. We apply a voltage to set V out is equal to 0 when VN1 and VN2 are equal to 0. And this output voltage is simply modeled as a voltage source that we place either in series with the input terminal 1 or input terminal 2. It does not matter which one, and it does not matter which polarity we choose. The reason why it doesn't matter which one or which polarity we choose is because inherently the DC offset voltage is going to be random. We have no way to know whether it's going to trend as a positive value or a negative value or anything like that. So let's take a look at a non-inverting op amp with an associated offset voltage. So I'm going to draw my op amp right about here. Seems legit. Positive polarity terminal, negative polarity terminal. Here's my feedback loop. This guy is R2. This guy is R1. Here is the out. And so in this instance, I am referring the offset voltage to the non-inverting terminal. So I literally just put a voltage source VOS for my offset voltage in series with my input, my actual input voltage that I'm trying to amplify. So you junior engineering students, what do you think is going to happen? I did draw it with positive polarity on the left, so sure. All right, so I think that's a reasonable explanation there. Let me change the polarity of this just to make things a little bit more obvious, because you pointed out a flaw in my way of thinking, right? Because of course you did. So the voltage applied at our non-inverting input terminal is simply the sum of VOS plus VN, right? Because this is a non-inverting amplifier, that means that we should expect to see that Vout is equal to 1 plus R2 over R1 times our offset voltage plus our input voltage. So in this case, our offset, assuming a positive value of the same polarity as our input voltage, gets amplified. If our offset voltage were negative, Brian is absolutely correct. It would actually wind up causing a lowering of the gain in the system. But either way, it has a negative effect. We're always amplifying the offset as well. Now, my question to you guys is, what if I applied the offset voltage and referred it to the inverting terminal? Anything change? No, not even a little bit, right? We could say that this voltage Vx right here is equal to Vout times R1 over R1 plus R2, and it is also equal to VOS plus Vn, and do an arbitrary amount of algebra and get the exact same result. That is why it literally does not matter if we refer the voltage to the input terminal, the inverting input terminal or the non-inverting input terminal. Doesn't matter what polarity we use, the effects are going to be the same. We're going to see that the offset voltage is amplified by the exact same amount, whether we put it in for the inverting input or the non-inverting input. So, all right, so with that in mind, let's break something. Make like it's 1997 and we're listening to Limp Bizkit. Let us look at an integrator circuit. And I'm going to refer my offset voltage to the non-inverting input terminal. Here I have my capacitor. Here's my resistor. And I am not going to apply a traditional sinusoidal or time varying input signal. I just want to see what the effects of an off-put voltage do to an integrator. All right. So, anybody think about what my transfer function should be for this guy, or what my input-output voltage relationship should be? Now notice that our input signal, which is the output, is being applied at the non-inverting input terminal, and everything that we derive was for something applied at the inverting input terminal. Okay. So, how I would approach this is I would say that this is nothing more than a non-inverting amplifier where we have some impedance Z2 in the feedback position and some impedance Z1 in the not feedback position, right? That's the easiest way to look at this thing. So we know that AV should be something around 1 plus Z2 over Z1, which is equal to V out over V in. So in this case, that's going to give us, in the time domain, V out is equal to VOS plus the integral, 1 over RC times the integral from 0 to t of VOS dt, where we are assuming that VC at 0, the capacitor voltage, is 0 volts. So we're just assuming, just to be clear here, that our capacitor is fully discharged before we connect this guy. My offset voltage is not a time varying quantity, right? It's a DC quantity. So that means that I'm going to have VOS plus VOS over RC multiplied by time. So can anybody tell me why this is a problem? Pardon? Overload the capacitor eventually? I mean, I don't like, there's a restriction on the amount of voltage that could appear at the output, right? Due to the saturation distortion conditions. So as long as your capacitor was rated properly, that would never happen. But you're getting close to it, right? As time increases, the output voltage drifts towards VCC plus for positive offset voltages, and it drifts towards VCC minus for negative input voltages. So you don't actually see, if we put a input signal in here as well, only the very beginning of the waveform would actually provide any integration. Over time, it's always going to drift to the supply rails, okay? So that is a very significant problem if we're trying to integrate a signal, right? Because we're gonna lose it. It's gonna fall to one of the supply rails. So what we can do to get rid of that is put a resistor in parallel with that capacitor. So that's going to look something like this. Offset. So here we have our capacitor just where it was. Here we're going to have some resistance R2. Here is our resistance R1. Here is our output voltage, V out. So at very low frequencies, our capacitor is going to look like an open circuit or very near it. And we should see that our output voltage is simply 1 plus R2 over R1 times VOS. So it isn't gone. We are still having some amplification of our offset voltage, but it's not forcing us to go to the supply rails. So we should still be able to see what's happening with our signal. So this begs the question, well, what does the inclusion of that resistor do to our integrator, right? So let's take a gander. Now, neglecting our offset voltage, the out, R2. Here's our capacitor C, R1, and here is our input voltage Vin. Again, I can say that V out divided by Vin, or our transfer function, should be something so in this case, we have an impedance of R2 in parallel with that capacitor in the feedback position, and an impedance of R1 placed between our inverting input terminal and ground. So this guy is no longer looking like a non-inverting amplifier. It's looking like an inverting amplifier based on where our input signal and all that stuff is. So this should look like negative Z2 over Z1, which is going to look like negative 1 over R1. So that takes care of our divided by Z1 bit. And then I'm going to have R2 in parallel with 1 over SC, which is going to be R2 divided by SC over R2 plus 1 over SC multiplying by SC over SC. I'm just moving forward in the math here. We are going to get R2 divided by 1 plus S R2C. So that's what those two guys in parallel look like in the Laplace domain. So previously we had a pole, dang it, there we went, at S is equal to 0. Now we have a pole at negative 1 over R2 times C. If our input frequency is much greater than our pole frequency, then this looks like negative 1 over S R1C, which is the exact same thing, the exact same transfer function that we saw for our integrator without that additional resistor in the feedback position. So I don't know, it tickles me to finally come full circle because I can remember giving you guys a design problem in circuits 2 where I asked you to make a multi-stage op amp where you had to convert a sinusoidal signal into a cosine signal or vice versa, and everybody that tried to do it with an integrator always saw that their output went towards one of the supply rails. And so I was like, you either need to put a resistor in or use a differentiator, and we have fully explained why a year and a half later. So wonderful. That's the last thing that I have prepared for today. I'd like to take a moment to look at our Webwork assignment for this class. So give me just a moment to pull that up, just to make sure I've done my due diligence to this point and we can answer some questions. So this closes on the 22nd, which is Monday at 9:30. All right. So problem 1 is an op-amp circuit that if I was feeling mean would have shown up on a circuits 1 test. It's an ideal op-amp, or I'm saying that you should treat it as an ideal op-amp because the title says op-amp ideal 03. So that seems reasonable to me. You have a current source in parallel with a resistor R1. So a source transformation puts everything in series and then it looks like a normal circuit. Easy peasy. Oh, okay. Yeah, okay. Well, yeah, to me, it literally says, hey, it's an ideal. So there's nothing saying it's non-ideal, like you're not giving a finite value for A naught. So I don't know what else you could do. Yeah. Problem 2, I don't know, can you divide 8 by 1300 and then multiply by 100? If so, you've got the answer to this problem. Problem 3, it's an integrator circuit, which I think at this point we have beaten to death. And you're trying to find the finite open loop gain given that you have a pole frequency at 1 hertz. Just remember that S is in radians per second. So all the equations and stuff that I've talked about pole frequencies are all based on angular frequencies. This is a linear frequency. So if you got the answer wrong because you tried it, it's because you forgot to either multiply or divide by a factor of 2 pi somewhere. So that one seems pretty straightforward. Problem 4, we did not cover inverting summing amplifiers in this class, but you could do this by just using superposition and treat it as two inverting op amps and then just add the results together at the end, or you can go back through and check your notes for how inverting summers work. Pretty simple and straightforward. Problem 5, we have a logarithmic amplifier. It's got an NPN transistor, so it's the one we covered in class. You're given the out, you're given the in, and you are trying to find the quantity IS times R1. So I feel like that's going to be pretty straightforward because there's not that many variables in that equation. And then lastly, problem 6 is something we actually did just a minute ago. So we would have 1.6 volts plus 0.07. So 1.67 multiplied by 1 plus R1 over R1 plus, no, excuse me, 1 plus R1 over R2. Easy peasy. And that is the full homework set. So I don't know, this might take like an hour tops, I would think at this point. So that's enough out of me for today. On Wednesday, we'll finish up op amps by talking about all the other non-idealities and all that kind of good stuff. So these would be like perfect things to expect to have to talk about on a job interview kind of topics. All right, you guys have a good, I was about to say weekend, but it's only Wednesday, so a good Thursday.